Hello, my name is Joshua Smith. I'm a fourth year computer science student, and today I'm going to be presenting a project that I've been working on for the last few months. This project is titled NJ Public Transit Prediction During the COVID-19 Pandemic, and it's by myself, Joshua Smith, and I have been advised by Professor Dr. Zheng. So a little bit of background for this project. The COVID-19 pandemic has been affecting almost all facets of daily life for 2 years. Besides the glaring public health crisis, the ramifications of COVID-19 include economic instability, divisive politics, and social unrest. I'm sure all of us have dealt with one of those three things over the last 2 years, I'm sure. A system which faced a particularly steep decline was the public transportation system. The Transit app is the most widely used public transportation application on the iOS marketplace. They recently released some data about their volume during the COVID-19 pandemic, and what was found after observation was that Transit app volume has been down an average of about 40% since the pandemic started. And that's just the last 2 years. If we were looking at only the first year of the pandemic, it would probably be about 50 to 60% down in New Jersey. Because of the immense volatility and instability that public transportation is going through, many inefficiencies have been reported. I personally have read articles about people waiting a long time just to have the bus come to the bus stop and tell them that they're not even allowed on the bus due to social distancing policies. There's also been, on the other hand, buses just driving around aimlessly without any passengers. Who wants to be on a crowded, tight space with people probably not even wearing their masks during a global pandemic. Predicting public transportation trends on a given day could be very helpful in remedying said inefficiencies. So that's the overall goal of this project. But in order to properly, predict transit volume on a given day, relevant daily data must first be collected. Using a multitude of sources, 13 attributes were found that I thought were potential candidates for affecting transit app volume in New Jersey. These include economic ones like gas prices and unemployment rates, but this is mostly a COVID-centric project. So there's a lot of COVID predictors in there, like total active infected cases, daily hospitalized increases, daily death increases, total active hospitalizations, negative test increase, daily positive test increase, day of the week, that's in the file as 0 through 6, month 0 through 11, weekend 0 if it's a weekday and 1 if it's a weekend, holiday 0 if it's not a federal holiday and 1 if it is, and then normal. Normal is a little bit complicated. It comes from the transit app data itself. Normal is, as defined by them, is the expected app usage without the pandemic as a percentage of the projected peak. So they come up with this projected peak based on last year's transit data, and then they adjust it for population inflation. And the normal is the percentage of that projected peak. And then the target attribute, which would be it's called actual, but it's just the transit app volume in New Jersey. And it's represented as a percentage increase or decrease relative to the calculated normal value. So it's just basically a percentage of the normal. And if it's below, it's like negative percentage. And if it's above, it's, plus percentage. That's how it's calculated. And before we get into the models overview, I just want to show you a little sample of the data here. Let's exit out of here and go to Excel. Okay. So here's the data. Here are all the attributes that I just discussed on the previous page. And then we have actual here in column M. That's the target variable, which is what we want to predict. So basically the problem that we have is, given these values for a given day, for a certain day, it could be any one of these days, and it could be a made up day, it could be any day with any values in here, can we predict what the actual COVID-19 public transit app volume is for that given day? And we have about 798 rows, 797 if you're not counting the titles. So we have a good bit of data. Let's go back to the PowerPoint. So to, complete this goal, we're going to be using some machine learning techniques. In this project, we use supervised learning, which is inputs and desired outputs are used for training. So as I just discussed before, all of the 13 attributes will be plugged in, and then the target attribute will be what we want to predict. And when we train the model, we plug both of those in. So, we can see what values correspond to the target output the best, which is the opposite of unsupervised, where you would just plug in the inputs without the target. And as I just discussed, takes two inputs: the set of the training data, which is the attributes discussed in the previous slide, and the set of target values corresponding to the training data. So we enter in all of this information into model training for supervised learning. So I'm going to be going over 3 of the models used and the results of their usage. So we have Model 1. Model 1 is a multiple linear regression model. So as you can see in the top right here, this is what a simple linear regression graph looks like. We have a bunch of scattered plots, and then the famous best fit line through all of them. I'm sure everyone has learned that in Algebra 1 at some point. But this can be extended into multiple dimensions rather than just just points and lines in one dimension. For example, this is what it would look like in 3 dimensions. It's points scattered in space, and instead of a best fit line, it's a best fit plane through those points. And we get that using this prediction formula. The prediction formula is used after the model's trained to figure out what our prediction is. So I'm going to go through and discuss each of the variables here. So H equals the transit app actual volume percentage. So this is what we want to compute. So H is the goal. What we want to find out is H. We feed all the H's into the model for training, but for testing we don't know H. So that's how we tell if the model is good or not. Theta is the set of attribute weights. Theta sub I is the weight of the ith attribute. X sub I is the ith feature or attribute. And the K equals day. So basically, what is the transit app actual volume percentage for a particular day with the set of weights and the set of features? And this is the equation how you would figure it out. So let me give you an example. Here, I'll pop back into Excel here. So say we wanted to find this negative 0.44. This is what we want to find, but we don't know that yet. All we have here is an H. So we don't really know what this 0.44 is. How can we get all of these values to add up to H? I mean, to add up to negative 0.44. We want H to equal 0.4, because if it doesn't equal 0.44, then then we have some error in our model, and that's going to reflect on the performance of our model. So you might think, oh, well, we have negative 0.44 already. Why do we even need to calculate it? But this is just for testing, and in a case where we don't have this negative 0.44 value, we're relying entirely on the model. So we need to ensure that the model is good. So how can we get all these values to add up to negative 0.44? I mean, it doesn't really look like it's possible, does it? I mean, we have this plus this. Even if some of them were negative, but I mean that you can't even do that. I mean, you know, the numbers as is adding up. It's obviously not negative 0.44. So that's like where the thetas come in. So remember back to the equation where each theta can be multiplied by x, which is the feature, to get that value as close to h as possible and even equal h. So, wrong one. So what can we times 1.89 by and then subsequently add to 4.8 times another something times 17, etc. And then how can we extend that to a whole data set, right? A whole data set of different values like this. So essentially, like, that's how the model is trained, where it sort of it tunes the model based on which is weighted the heaviest. So for instance, I'm pretty sure unemployment rate is like a pretty heavy weight, so this 4.8 is going to be multiplied by a larger number than the gas price, because the gas price doesn't really matter. The gas, you would think the gas price matters, and maybe it does matter. I'm just using this as an example, but the unemployment rate matters so much more than the gas price, so therefore it will be multiplied by a number whose absolute value is larger than the natural gas price, or the national natural gas price, I should say. So yeah, that's basically how the linear regression prediction work, and that's almost essentially how the training works as well. So basically, training is finding the best set of these thetas such that the cost or the error is between this calculated value h, because this value h, it could, after applying the model that's been trained and predicted, you could come up with negative 0.35, and obviously that's different than negative 0.44. Let's say it's 0.34, and then the error between the two is 0.10. So I mean, that's like pretty decent. I mean, 0.1 is the error between the two. It's just the difference, negative 0.44 minus 0.344. And that's the absolute value of that. And so we want to find a set of thetas that, for as many of these as possible, when you take this and extend it to tons of examples, we want to get this error as low as possible. So there could be a set where it's 0.05, or there could be a terrible set where it's like 0.90 or something, whatever, 0. Or like 20, or 20. That would be terrible. So it's just a matter of how do we minimize the cost of prediction. And that's what we did. So I coded this in Python, and I'll show you some of the results here after I pull it up on Python. Here's what we did last time. So I have some just code here, simple pre-processing. We scale the data between 0 and 1 and negative 1, just so that the model can digest it better. Then we split it into 80-20 train test size. So we want 80% of the data is used for training. I think that's like 528 or something like that. Yeah, I think that's it. And then 20% is used for testing. So 20% of the data is even touched for training. It's just used for testing. And we're about to see that in a second. Then we just use some linear regression here from Python libraries. And yeah, we have some results and visualizations for you. So let's run it. Okay, so here's just a nice little bar graph I made. It's not really anything special, but it just shows you 20 random experiments out of the 797 minus 528, so however many that is, 160 something experiments. So yeah, as you can see, like this one is pretty off, like 0.9 to 0.65, like that's pretty bad. This is like way off, but other than that, it's pretty close, which is nice. Obviously we're looking at the predicted versus actual, transit app volume percentage, where the bar graph is the predicted and the blue is the predicted and the orange is the actual. So this is just what that looks like here. So as you can tell, most of them are negative due to most of the data sets coming in from data which was collected post-pandemic, so most of the time it's just down. Sometimes it's up. And then we have another visualization here, which is interesting. It's the attribute weights. So these are like the thetas that I've told you about. So after scaling all the data from -1 to 1, we find that unemployment rate and positive increase are the most heavily weighted attributes when it comes to figuring out what that actual value is. So I was saying in the Excel sheet, I guess it really was like the Excel sheet where unemployment rate is going to be multiplied by a much larger number than gas price if gas price doesn't matter as much as unemployment rate. So it looks to seem as though in this instance the model has classified the unemployment rate as like a massive indirect correlation with the transit app volume, which is something that if you just like thought about it, you would expect. As unemployment rate goes down, the transit app volume you would expect to go up, and then vice versa. If unemployment rate is skyrocketing, then no one's going to be getting on a bus to go to work or a train, so it's going to be going down, the volume that is. Same thing with positive increase of tests. Same sort of logic. As the positive test increase daily goes up, that's like a pretty big signifier of how the pandemic is going. Not necessarily like how many people in total have tested positive, but rather how many people are testing positive per day in New Jersey. So if there's like upwards of, I remember it was, I don't know how it is now, but I remember some big numbers were like 4 grand. I'm sure it's like much higher now with the Omicron. I just haven't looked. But as the positive increases, test increases go up, then you would see the transit app volume go down, and then same thing, vice versa. So this is what this model has classified to be the more important ones, and it seems like the rest were negligible. Hospitalized currently, death increase, same sort of thing. And then we just have some values here that of like the 160. We have some here that you can just compare real quick in the terminal. Predicted negative 0.56, actual negative 0.49, predicted negative 0.87, actual negative 0.65, predicted, same thing. So it looks pretty close. There's obviously some discrepancy, but in general, you kind of want some discrepancy because if not, then you're kind of setting yourself up for overfitting the model and just like memorizing the data per se. But it's good to have some discrepancies there. And then we have the errors, and I'm going to go into that in the PowerPoint. So model run results. So we have the mean absolute error, mean squared error, and the root mean squared error. I'm just going to take a drink real quick. And these are some common accuracy metrics for determining how good, per se, a model is. So I'm just going to go through what these are real quick just so you know. The mean absolute error is in testing, the actual value minus the predicted value, the absolute value of that, and then you just you add them all up and then average all of them. So you just take what we've seen in here, this value minus this value, add it up with all of the other differences, and then average by, however many there are. And then the mean squared error, same thing except for it's squared. And then the root mean squared error is the square root of the mean squared error. And these are all just common accuracy metrics that are pretty universal to machine learning. And typically the smaller they are, the better. So a good indicator is the root mean squared error, and it's like if it's closer to 0, it's better. So this model, it looks pretty good. Okay, let's go to Model 2 now. So Model 2 is a little bit more complicated. It utilizes a neural network. I have the architecture of this neural network up here in the top right. We have 7 layers here, most of which are activated by the rectified linear unit function, which is shown below. The output shape is like the neurons per lever, so there's like 32, 1 by 32, so that just means there's 32. It's like a one-dimensional shape. It's not like 2-dimensional or 3-dimensional or anything. So there's 32 neurons, and then 32 neurons, 16, 8, 4, 32, and then output as 1. The number of params is the number of weights per layer. Think of like thetas, but just more of them, and are connected to each neuron once. So, this 32 times multiplied by, I think 13 is 416, so it's like the 13 attributes times the 32, and it goes to all the rest of the 32 neurons in the next layer. The 13 attributes go to each one of the 32 neurons, and that's 416 parameters, and then the same thing for the rest of these. And then the activation is the neuron activation function, which is the rectified linear unit function, which basically means a neuron has an input and output. And if the neuron's input is a negative number or 0, it returns 0. And if the input to the neuron is a positive number above 0, then it just returns that positive number. So not only does it, so if it's negative, 0, and if it's positive, it's sort of like a light, which you can like adjust the dimness of it. So you can turn the light off, or you can like slowly make the light brighter. So it sort of is a good way of measuring intensity. And then optimization is the atom optimizer that you just use. It's just a specific utilization of stochastic gradient descent, which is just some calculus stuff for weight tuning. So basically, the neural network outputs something, and then it just tests to see whether or not it's like what, just to see if it's like a valid prediction. That's what like a validation set is used for, and then it sort of goes back on itself and back propagates through the network, and then tweaks the weights again, and then just goes back and forth until it is satisfied with the output, and it's close. So I'm going to go through the code of that. Okay, so same sort of thing, same setup. Instead of like standardization here, we use min-max scalar for pre-processing. So it still changes the values to like uniform, but it just uses like an equation for like it takes the maximum minus the minimum, and then changes it from into small numbers, but still distributed evenly. So if it's like say the range of the specific attribute is like 100 or 1,000 to 500, then it takes all the values and just like changes them into smaller numbers, but still has like an even distribution from the smaller numbers as it did from like 500 to 1,000. Same thing here with the train and test split. We want 80% and 20%. This time we need validation sets for, as I just mentioned, optimizing the neural network. And here's as I just discussed, this is the architecture of it. Same exact thing as here. So yeah, let's run it. So it's training now. Okay. So let's take a look. Same sort of deal. 7266.2022.07.02. Like, it's pretty close. Same sort of thing as the linear regression model. I think the accuracy metrics are relatively similar as well. Mean absolute error is a little lower, or a little lower. Yeah, these two are a little higher, but it essentially looks like pretty similar to the multiple regression, which is interesting. I'm not going to say, I'm not sure whether that's like a good thing or a bad thing, or it's not either a good or bad thing, but it's interesting nonetheless. So finally, Model 3, the last approach. So this was very high level, meaning I didn't really have to do much by hand. There was still obviously some coding that went into it, but this is a library that is made specifically for Python machine learning called AutoGluon, and it's a very useful library for tabular machine learning. Basically does everything for the programmer, and for some complex stuff that it's doing, it's very user friendly. And it utilizes a special type of model tuning called stacking, which is what you see on the right. So basically, a ton of different regressors, neural networks, are used concurrently together, and they each make their own prediction. And then all of those predictions, this is actually what they're called for the one I use. We use the Cat Boost, Extra Trees, K Neighbors, Light GBM, Neural Network, Random Forest Regressor. We use all of these neural networks. They each make their own separate prediction, and then it goes into another a weight, and then from that weight it goes into the final prediction. The model weighting is just another calculation to turn all of these 6 predictions into one value. So for example, it could be the average, and I'm sure it's a little bit more complicated than that, but that's just an example, I'm sure, especially if there's like large outliers. Yeah, so many models are used concurrently and then compared to give a super accurate result. That's what their marketing is, I guess you could say, is very accurate. So let's take a look. Are they accurate? Oh, right. Yeah, so I had to run this on the Linux subsystem on Windows because it's actually not made for Windows. So I had to like download. Oh. Okay, there we go. So I just coded in here, same sort of thing, loaded into the data set. Does basically almost everything for you. Just got to drop the column. You can tune some options here for the neural network, like the epochs and some GBM options. You can set a time limit because it takes forever to train with the stacked models. I have the time limit set to 2 minutes. That says 2 times 60, but it could go a heck of a lot higher. Luckily, it lets you store the model in a directory so that instead of every single time training it, you don't have to sit here and wait for me to run it every 2 minutes. Let's hide that. So yeah, same thing. I just load it from the storage, and then same sort of deal. I predict and then run the results. So let's check this out here. Okay. So let's take a look. Same sort of deal. 0.52, 0.55, 7, 5.3, 5.4, 5.6. I'm seeing a lot of the first numbers being the same, which is like pretty good. Like, or first number after the decimal. 4.9, 4.9, 5.7, 5.3, 5. I mean, that's like pretty good. I like seeing the first numbers afterwards, after the decimal being the same for predicted versus actual. And then here we have our root mean squared error. They have negatives because they just like to be fancy with it and show that it skews one direction. But typically these values aren't negative. But I can take a look at that in. Yeah, we don't really care about the negative numbers. We just care about the absolute value. Autogluon is basically just saying that it negative, it skews like below the actual. Like the predictions are typically lower. I think if it's like, depending on how they do it, I'm not really sure the back end of it. They could do predicted, actual minus predicted, in which case it would be, it goes over. So maybe it's like the predicted is a little bit higher than the actual. Regardless, it just shows that it skews one way. So let's go into here, yeah. So the mean absolute error, 0.044, mean squared, 0.0033. So these are like pretty low compared to the other ones. If you remember, I think it was like 0.1 root mean squared error for the other two. Let's see. Yeah, 0.11. This is like 0.05. So that's like, by a factor of 2, it looks like cut by a factor of 1/2 or whatever. That's pretty good. Yeah. I mean, obviously like overfitting is a concern, but I've used Autogluon before for other things. I haven't really seen an issue, but I'm definitely going to pursue more testing with this to make sure that these are correct. So, conclusion. The potential for scalability, given the accuracy of the predictions, the data set can easily be extended to other states, specific cities, small countries, all the data that's available on the Transit app. We can just find the corresponding data for those specific countries, and very easily scalable. Could be done very easily now that we have the sort of the formula for how to do it in mind. And definitely the next steps for these projects, or for this project, like the potential next steps. Like I've already done this project, and I feel like I'm very satisfied with the work that's been done, but I think that you can definitely extend it more. Like for instance, like run a simulation where the models advise how many vehicles to run each day. Using the predictions, we say, okay, how do we translate that into, okay, how many buses do we run if the Transit app volume is down this percentage or up this percentage, depending on the COVID cases, unemployment rate, etc. And then more visualization of data, interactive charts, website deployment, just something to look at all the data and say, here's what we found, besides obviously a PowerPoint presentation, but just something that we can get everything together and show it. That, especially with the website deployment, interactive charts, the whole other projects in of itself. But yeah, these are definitely the potential next steps for this project. Thank you for watching this. Thank you also to the BOT for sponsoring this project, and thank you to Professor Dr. Zheng Li for helping me out. I'm actually in the midst of submitting a paper for this project to some journals, see how they like what work I've done. So definitely thank you to him. Here's what the paper looks like a little bit. I'll just give you a little sneak peek here, but yeah. Yeah, definitely BOT. Thanks a lot. And here are my references. These are the same references that I use in the paper. All of these were used in this presentation today for, whether it be I talk about or the data collected. These references were very helpful. And then my contact information, smith113@go.stockton.edu. If you have any questions about the project, I will respond quickly. So thank you, and have a good day.